This is mini excursion number 5 for Finite Math A. Today we are talking about ciphers and codes. Your job today by the end of this video is to understand the difference between a cipher and a code, and then to encode and decode, to encrypt and decipher several different common ciphers and codes. So what is the difference between a cipher and code? Well, in non-technical terms, to your average person, there really is no difference. To a cryptographer, somebody who studies ciphers and codes, there is a big difference. So let's start with a code. A code is a string of random symbols or numbers. Each symbol stands for another symbol, another letter, or another word, and you have a code book used as reference. Each symbol is translated one at a time until the message is complete. So for example, if you were going to use our 26-letter alphabet and we're going to use a code for the 26-letter alphabet, you would have to have a code book that had 26 symbols in it. The symbols could be other letters scrambled up in some random way, or they could be symbols like pictures, like hearts and stars and dots and things like that. So a code, one letter at a time, is encoded or decoded from a code book. Each letter stands for another letter, and there really is no way to figure it out besides using that code book. One of the most common codes, or most famous codes maybe, is called Morse code. And you probably have heard of Morse code before. Everybody's heard of the SOS, and we're trying to use lights and dashes. And you've seen some movie where somebody's tapping on a pipe and they hear the Morse code, etc. This was invented by Samuel Morse, who was the creator of the telegraph. Telegraph was used with dots and dashes, and these can be communicated by light or sound. The International Distress Code is SOS. That stands for Save Our Ship, or Save Our Ships. This was used on water vehicles to use light to send the distress code that way. Another really funny, have you ever heard of an SOS pad? That is used as a little scrubby thing for the kitchen. Those came out and their lingo was Save Our Saucepans. So they used that to kind of help themselves out. SOS pads. Experienced operators of Morse code can actually communicate without writing anything down at about 20 to 30 words per minute. So they can hear the letters and they actually can string those together in their heads. If you want more information about Morse code, there's a lovely little link here. Now here is the Morse code for our 26-letter alphabet, plus a couple of extra symbols here that you might find useful. This is just a small sampling. There are actual Morse code for the @ symbol for like to communicate a website or an email address. There are other symbols that are used as well, but just for kind of get an idea. And I found this article in the paper, this comic in the paper, and I just love Foxtrot, because there's always something smart about Foxtrot. So whereas we're watching along and the author has, tap, 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 and he's tap dancing, Jason is tap dancing, and it says, so are they going to let you in the talent show? Nah, one of the judges knew Morse code. So I'm a little bit of a nerd, and I thought, I wonder what it says. So I immediately went and looked up a Morse code and started translating. And that's what we're going to do. So I see tap and I see tap. So I'm assuming that tap is a dot and tap, tap, tap is a a dash. So when I see tap, 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 I'm thinking dot, dot, dot. And I look up dot, 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 and that is an S. All right, and I look up the second symbol, tap, tap, tap. That is a dash, dash, dash. And I get an O. Okay, the next one says tap, tap. That's a dash, dash. I look around. Oh, there it is. That's an M. And the last is a tap, short one. That is a single dot. I'm looking for my single dot. That is an E. All right. And now I'm going to ask you, or ask the substitute for this lesson, or if you're watching this on the website, I'm going to ask you to stop for a minute and pause this video. And I want you to take about 2 or 3 minutes and try to translate the rest of this message just like I did. So again, we're looking at the next one, tap, 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 would be dash, dot, dot. I'm looking for dash, dot, dot, dash, dot, dot. Where is it at? There it is. Dash, dot, dot is a D. So each one of these little frames will have 2 letters. Okay, so again, I want you to pause the video and try your best. All right, I'm back. Video unpaused. Everybody's got a message. And if you get through this, you will translate all the way. It will say some Y day I W I L L R U L E Y O U A L L. And so we have this funny little message from Jason that says, someday I will rule you all. All right. So that's good times there. All right. So again, Morse code. This is a code because without the code book or without knowing what each symbol stands for, you can't really break this code. I have to translate each symbol one at a time. There's no way to look at what I have and just know what it is unless I have memorized the code book. Okay. Another famous kind of code that you're used to seeing probably on a daily basis, whether or not you realize it, is an ISBN number. This is called an International Standard Book Number, and it is a code because every single book that is published has a 13-digit number that uniquely identifies the book. It also works with book-like products and audiobooks. They call them bookland items, printed, audio, videos, etc., is assigned a unique code that can be read by computers at libraries and retailers. So every single book, if you know the ISBN number, then you can find all the information about that book. So there's a huge storage informational place where this server, computer server somewhere, has all the information. Every ISBN number is recorded for every book that has been published since a certain time period. So each ISBN number actually does tell us information. It's not just random. The prefix 978 is assigned to all bookland items. They also have things called music land. So if it's a published book that is full of music, usually it will start with something other than 978. But book items are 978. So the first 3 digits there. The next is the group or country identifier. Each national or geographic grouping of publishers has a 1 to a 5-digit number that could go next. So the group number comes next. 0 or 1 is used for English-speaking countries. 2 are French-speaking countries. 3 is German. So the smallest numbers actually go to the biggest countries. And then if you wanted to look at a book from the area of Bhutan, that would be 99936. So the next set of numbers again represents that group number. Inside each of those group numbers is a publisher identifier. So in the 0 group, which is your United States group or English speaking in the United States, the next couple of numbers tells you whose publisher it is. So the next, for example, 00 is HarperCollins, 07 is McGraw-Hill, 389 is Barnes & Noble. So these are the publishers. The reason why the bigger countries get these smaller numbers for their country identifier is because there are more publishers in those countries. And then the last one is a title identifier. So it is a particular title or edition of that title. And then the very, very last number is something called a check digit. All right, now the check digit actually doesn't really represent anything. It is a way for the computer system to make sure it hasn't made a mistake in reading the title of the book. So it also helps with counterfeiting and things like that. So to calculate a check digit, you take the first 12 numbers in your ISBN number, which actually stand for real things, publisher, country, language of origin, those kind of things. And you multiply the digits alternately by 1 and by 3. Now let's look at this ISBN number right here, and let's go ahead and do this. So I'm going to take the digits, and I'm going to do 9 times 1, and 7 times 3, and 8 times 1, and 8 times 3. Okay, that puts me to there. Okay, and then 1 times 1, and 7 times 3, and 5 times 1, and 2 times 3. Puts me to there. 5 times 1, and 7 times 3, 6 times 1, and 6 times 3. So I alternate every other digit starting with 1 and 3, and I multiply those digits. Now the next thing I do is I find the sum, and this is a special word, sum modulo 10. So I'm going to take these and I'm going to add up all of these little products. Okay. So I'm going to start off with the sum. Okay. And you're going to want to probably grab your calculator. So in my calculator, I'm going to type this in, and I am typing this in as I am making the video, so I am sure I will make a mistake. So I'm going to do 9 times 1 plus 7 times 3 plus 8 times 1 plus 8 times 3 plus 1 times 1 plus 7 times 3 plus 5 times 1 plus 2 times 3 plus 5 times 1 plus 7 times 3 plus 6 times 1 plus 6 times 3. I'm nervous. I end up with 145. Okay, so that's my sum. But what I'm looking for is something called the sum modulo 10. The sum modulo 10 is modular arithmetic is something that we often call clock math. It's when you have numbers that repeat over and over again. What you're not really interested in is the actual sum of the numbers. You're interested in the remainder after division. Like take, for example, on a clock. If it's 3 o'clock and I want to know what time it's going to be 10 hours later, I don't say it's going to be 3 plus 10, 13 o'clock. I could add them in my head, though, and I could say, okay, it's 3 o'clock, 10 hours later, that's 13 minus 12, because there are 12 hours in every cycle, and I would end up with 1 o'clock. Okay, that's kind of what we're going to do here, except for we want mod 10. So I'm going to take 145, and I'm going to divide by 10. That 10 goes into that 14 times, giving me 140, with a remainder of 5. That 5 is the number that we want. That is 145 mod 10. Or in other words, that is our number with the remainder after division by 10. So I'm looking for how much is left over when I divide by 10. And then finally, I subtract that result from 10. So 10 minus 5 gives me 5 as well. That is my check digit. So every book, if you go through this, this is what the computer does. Every time it scans the number, it can look up exactly what the book is, and then it runs through this information, it calculates this sum, and then spits back the check digit. And as long as that matches, then it knows it has found the right book. But if that information doesn't match, then we know that we have a mistake. All right, so here's another one. It says find the check digit. Okay, so I'm going to start off alternating. So I'm going to take 9 times 1 plus 7 times 3 plus 8 times 1 plus 0 times 3. All right, that gives me the first 4. And back to 3 times 1 and 8 times 3 and 5 times 1 and 5 times 3. That's there. And then 2 times 1 and 8 times 3 and 0 times 1 and 4 times 3. So I'm going to find that sum. So in my calculator, I'm going to type in 9 plus 21 plus 8 plus 0 plus 3 plus 24 plus 5 plus 15 plus 2 plus 24 plus 0 plus 12. And I end up with 123. Okay, so that's my sum. The next thing I want to do is find the sum mod 10. So you might be able to say, well, 123 mod 10 is 3, because the remainder after division by 10 would be 3. Or if you want to do the division, it would look something like this. How many times does 10 go into 123? It goes in there 12 times. That's 120 with a remainder of 3. So modular arithmetic gives me the remainder. The very last step in confirming the check digit is to subtract that mod from 10. So I end up with 10 minus 3. So I get a check digit of 7. Okay. So again, an ISBN number is a type of code. Every book is encoded with this number. In order to find a certain book, you have to know exactly what the code is. So a code, one symbol at a time. There's some code book that you can look up to. A cipher is a different story. A cipher takes a message which we call plain text, something that's plain to read, and you apply a set of rules to it. That helps you translate it into something called ciphertext. You need to understand how to get the ciphertext by some sort of key. The sender and the recipient both must have the key. Now, this is better than a code book because sometimes ciphers can be very, very simple. A very simple rule, and you don't necessarily have to memorize the entire code book. You just have to memorize the rule. So a Caesar cipher is probably the most famous one of these. Actually, Julius Caesar used this to communicate with his generals, and it was just mind-boggling to them. No one could break it. In the time before modern computers, this was just amazing. Nobody had any idea what was going on. They could change the key at any time. A Caesar cipher takes each letter in the alphabet, and it shifts it forward a certain number of spaces. That number of spaces is the key. So, for example, if I wanted to encode this message, I think I will dance this weekend, then I am going to take and I'm going to move forward 3 spaces. And I'm worried that by zooming in, I've taken this off the screen. So I'm going to zoom back out again. Okay, so I'm going to move forward 3 spaces. So I start with my I, and I look up at my alphabet, and I go forward 3. 1, 2, 3. That is an L. And then T, 1, 2, 3, W. H, 1, 2, 3, that is a K. I, 1, 2, 3, that is an L. N is a Q. K, 1, 2, 3 is an N. And so we would do this for the entire message. And if you want to make it a little clearer, you could put slash marks through it. Let's see, I, 1, 2, 3, that is an L. W, 1, 2, 3, that's a Z. I, 1, 2, 3, that's an L. L, 1, 2, 3, that's an O. Got 2 of those, so it looks like ZLU. That's exciting. All right, D, 1, 2, 3 is a G. A, 1, 2, 3 is a D. N, 1, 2, 3 is a Q. C, 1, 2, 3 is an F. And E, 1, 2, 3 is an H. Now, since we're doing this by video, I'm going to stop at this point. But if this was a real thing I wanted you to encode, I would want you to continue out throughout the entire thing. Now, there are a couple of letters that you do need to be careful about. Anytime you have something at the end of the alphabet, it may need to wrap around back at the beginning. So, for example, if I wanted to encode a Z, then I would have to go forward 1, 2, 3. Z would turn into a C. Or if I wanted to talk about Y, I would have to think, okay, 1, 2, 3, Y would turn into a B. So if you might have to wrap around the end as you do this. To decode a Caesar cipher, you need to work backwards. So I would start with my H, and I'm going to work backwards 7 letters. 1, 2, 3, 4, 5, 6, 7. That's an A. And I might scan ahead. Do I have any more H's? Nope. J. 1, 2, 3, 4, 5, 6, 7. That is a C. V, 1, 2, 3. Oops. V, 1, 2, 3, 4, 5, 6, 7. That's an O. T, 1, 2, 3, 4, 5, 6, 7 is an M. W. P. And if we were to continue one at a time working in that direction, this comes up to say a complete mess. Okay. Now, a Caesar cipher is different from, say, a cryptoquip, which they sometimes have in the paper, where you would say, okay, the A is an H and the B is a W, where one letter stands for another letter. That is a code. The Caesar cipher is a shift in these letters. So when we're dealing with this, it really is an algorithm. The only thing you have to know is how many letters you're going to shift forwards or backwards. Now, this is a complete mess, however. Caesar cipher is very easy to break, and in our day of modern computers, you might as well not even try to use a Caesar cipher. A simple computer program just tries all 26 keys. you know, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way to 26 to see how many letters it's shifted. And they can tell right away how to break the program. If you were to use, for example, E is the most far frequently used letter in the alphabet. So all you need to do is do a quick text analysis, figure out what the most frequently used encoded letter is, and then guess that that is E. So, for example, if you see that A happens more often than anything else, then you probably know that A equals E, and then you're on your way to breaking the cipher. So this is a very confusing thing for somebody doing this by hand. It was great for Julius Caesar when they were giving handwritten messages, but for a computer, we just really don't want to do that. Sometimes you can use a cipher wheel, and on the cipher wheel, you scramble it. That turns your cipher into a code. So instead of making the alphabet go in order, you still use some sort of key where you match up the A and then you shift it, and then the second one doesn't match. But even with a scrambled alphabet, over time, you just do a frequency analysis, and you're going to have that broken. So Caesar cipher is not great. So here's another version of a Caesar cipher. This is called a Visionnaire cipher, or there's a version of it called a Playfair cipher as well. And what you do is you have a key word that represents a series of shifted alphabets. So the keyword that we're going to use is Leahy, L-E-A-H-Y. And we're going to write this over the phrase we want to encrypt. Okay, what we have over here is we have our key letters. Okay, so these are our keyword. And up at the top, this is our plain text. Okay, so those gray letters are our plain text letters. And in the middle right here, this is where our cipher text is going to come from. Okay, so these are our cipher letters. Basically, the process that we're going to use is we're going to decide which key letter we have and which plain text letter we have, and then see where those cross. Now, I know this says discrete math because that's what this class used to be called, but so think about that. You love discrete math. We're going to start off and we're going to write the letters of Leahy, our keyword, above each of these letters. Okay, so we just keep going one letter at a time. And if you get to the end and you don't have enough letters to finish, that's fine. You just keep writing it. All right, so I'm going to start, and I know my key letter is L, and I'm looking for a plain text I. So I think, okay, I'm looking at this row and this column, and those intersect at the letter T. So this I becomes a T. Now notice later on I have an I. That's not going to turn into a T because it uses a different code letter for that. Okay, the E, I'm looking for the letter L. So where L plain text intersects with key letter, that would be a P. A tells me which row to use. H tells me which column to use. And those intersect at H. H tells me what row to use. V tells me what column to use. Those intersect at C. And I've just got myself very confused, and I think you did as well. Let me back up here. I don't know what I was thinking. I was looking at the AH and not the O. Okay, everybody pretend like I didn't teach it that way. Let's go back. The A tells me what row to use, and then the O tells me my plain letter. O, that should intersect at O. How about that? That's better. Mrs. Leahy is tired. All right, here's H and V. That would be a C. All right, sorry about that. Confusion, override. We have row Y and plain text letter E that intersects at a C. And this is how I knew I was wrong, because I remember this says TPOC. All right. Now I'm going to go back to the L. I'm looking for plain text letter D. Those intersect at O. And cipher letter E. Key letter E. And plain text letter I. And I've got an M. So see how nice this is, because before I stood for T, and here I stands for M. So it's not as easy for a frequency analysis to be run because we don't know, we can't say that the I always stands for the same thing, so it's not a code. In key letter A and cipher letter S, We have key row H and plain text letter C. We have key row Y and plain text letter P. Sorry, R. We have key row L and plain letter E. And like here I have two P's, but neither one of them, here's another one, none of them stand for the same letter there. E is my key letter and T is my plain text letter. That's an X. A and E intersect at E. H and M intersect at T. Y and A intersect at Y. And L and T intersect at E. E and H intersect at L. So you can send the message, I love discrete math, by saying, Tapak Tayel. And we can spell this out. And you could make it even more code-like or more cipher-like if you got rid of the spaces in between and just sent this random string of letters. All right, so to use a Visionnaire cipher, again, you use your row and your column and see where they intersect. All right, so let's do another one. We're going to do Avon, and we're going to use that to encrypt the Hoosier state. Now, just to take a note at what's going on here, notice that when I have this shifted alphabet that says Avon as my key, what I've just done is there's A, B, C, D, etc. V, V, W, X, Y, Z, and then it starts over at A. O, P, Q, R, S, it starts over. So this just is the alphabet shifted to start with this letter. As soon as you hit Z, you start over. All right, so I'm going to take Avon, A, V, O, N, A, V, O, N, A, V, O, N, A, V, O. I don't get all the way to the end. That's okay. Remember that this is my plain text up here. And so what I'm trying to do is look for the right key and the right plain text letter, and that will intersect at the code that I need. All right, so code letter A and plain text T intersect at a T. Code letter V and plain letter H intersect at C. Code letter O, plain E intersect at S. Code letter N, plain letter H intersect at U. Code letter A, plain letter O, intersect at O. Code letter V, plain letter O, intersect at J. Code letter O, plain letter S, intersect at G. Code letter N, plain letter I, intersect at V. Code letter A, plain letter E, intersect at E. Code letter V, plain letter R, intersect at M. Code letter O, plain letter S, intersect at G. So that's interesting. We had two of those line up perfectly. Code letter N, plain letter T, intersect at G. Code letter A, plain letter A, intersect at A. Code letter V, plain letter T, intersect at O. Code letter O, plain letter E, intersect at S. All right, so this is called our ciphertext. That's our encoded message. The Hoosier state was our plain text. But it doesn't do you any good to just be able to write one of these. You also have to be able to decrypt them as well. All right, so let's think about what you would have to do to decrypt. Now, the thing that you would know as one of the code breakers, okay, is you would know the keyword. That's something that both you and the code sender would need to know. So you definitely know the keyword. And if it comes to you encrypted, you would know the cipher letters, which means you would know these areas in between. So you would know the keyword, Okay, so you take your key and you would look for your cipher and then look up to find your plain text. Okay, so instead of seeing where they intersect, we're going to look over and then look up to find the plain text, because that's what we want. So a Visionnaire cipher with the keyword luck was used to encrypt. So I'm going to start off and I'm going to put the word luck above this several times. All right, and I run out of room. All right. So I'm going to start with row L, and instead of looking for the plain text, because this is not the plain text, this right here is the cipher, I'm going to look for the letter D. So here's my key row L, looking for the letter D. Here's D. According to that, I would look up the plain text letter I want is an S. Here I'm looking at row U. I'm looking for a cipher letter Y. Here's my cipher letter Y. That cipher letter Y would have come from a plain text E. Here's my code row C, and I have a cipher text P. There it is. I look up, that would have come from a plain text N. I have my code row K, and I'm looking for the ciphertext S. That would have come from an I. Code row L, I'm looking for Z. There it is. I look up. That came from a cipher letter O. Code row U, I'm looking for a ciphertext L. There it is. I look up. That gives me an R. So this first word is senior. Okay. Code row C, I'm looking for a ciphertext U. There it is. That comes from the letter S. Code row K, I'm looking for a ciphertext U. There it is. That is a K. Code row L, ciphertext T. I look up. That came from an I. Code row U, I'm looking for a ciphertext J. That came from a P. Senior skip. Code row C, ciphertext F, comes from a D. Code row K, ciphertext K, comes from an A. Code row L, ciphertext J. Where's the J? Oh, it's way down here. Comes from the Y. Senior skip day. All right, so that is our way of decoding. So if we're talking about the Visionnaire Cipher, you're going to be doing one of two things. You're either going to take your key word, your plain text word, and you're going to see where they intersect to get your cipher, if your cipher is what you want. If you are going to decode, which means you have the cipher, you would take your keyword, you would look for the cipher, which is what you have, and then look up to figure out what the plain text was. So if you're looking for the cipher, you're looking in the middle. If you're looking for the plain text, you're looking towards the top. So you have a little worksheet. The worksheet is going to take you a couple minutes to do, and you're going to have several different kinds of ciphers and codes on there. And the important thing is to understand the difference. So the difference between a cipher and a code is one letter translated one at a time from a code book. And there's no real way to determine what those symbols mean. A lot of times they're arbitrary. A is F and B is C and C is Z. There's no pattern to them. Or possibly you have a symbol like Morse code, or an ISBN number where the code actually stands for a book. So a code is one thing stored at a time. You have some sort of general bank of knowledge. A cipher is a set of rules, and the rules require some sort of key, and once you know the key, you can use your rules to translate and to decode. So, for example, Caesar cipher is when you shift the letters forward. A Visionnaire is a series of shifted forward letters. Or maybe you create your own set of rules, like I'm going to skip 2 letters forward and count 3 letters back, and then I'm going to flip the letter back and forth 3 times or something like that. You have create your own set of rules, but a cipher is a series of rules, whereas a code is a set of one symbol at a time translations. Good luck.